Welcome to Hot Chips 2023. Session 2, CPU 1.
So let's start with the first talk of the session, which is first of the section is by Magnus Bruce, and this talk is going to be on Magnus is going to talk about ARM and ARM's Neoverse V2. And Magnus is a lead CPU architect and fellow at ARM and is based in Austin. Over the last 12 years at ARM, he has been part of the design team that created the Neoverse and Cortex CPUs and contributed to ARM and AMBA architecture. His work focuses on high-speed, high-bandwidth CPU memory subsystems, coherent interconnects, and CPU-to-system interactions. He got his bachelor's from and master's in electrical engineering from University of Florida. So let's welcome Magnus.
Hello, I'm Magnus Bruce. I'm a lead CPU architect and fellow at ARM, based out of Austin, Texas. And I'm here to talk to you about the Neoverse V2. So ARM is a global semiconductor design and software leader. Our energy-efficient processor designs and software platforms have enabled advanced computing in more than 250 billion chips to date, and 30.6 billion chips in financial year 23 alone. ARM technologies securely power products from the sensor to the smartphone to the supercomputer, providing a trusted foundation for a vast range of applications. Together with more than 1,000 technology partners, ARM is defining the future of computing. Okay, enough marketing. ARM's Neoverse CPU products are aligned across 3 product lines: the V series, the N series, and the E series. The V series aims for maximum performance and optimal total cost of ownership, targeting cloud, HPC, and AI ML workloads. The N series targets scale-out cloud, networking, DPUs, 5G, and other markets through a focus on efficiency. And the E series complements V and N by providing throughput-oriented efficiency. But today, I'm going to be talking about the V2. Later today, though, my colleague Anitha Kona is going to be introducing the N2 compute subsystem, a complete CPU and memory subsystem suitable for creating customized SoCs from a variety of markets. So, Neoverse V2 products were created with a focused set of design goals that define how our pipeline operates. The foundation of this pipeline is a run-ahead branch predictor, and this branch predictor acts as an instruction prefetcher, and it decouples fetch from branch. Large branch prediction structures provide coverage of very large, real-life server workloads. We use physical register files that are read after issue, allowing for very large issue queues without the burden of storing data, and this is necessary to unlock ILP. We use low latency and private L2 caches, low latency L1 and private L2 caches with state-of-the-art prefetching algorithms and aggressive store-to-load forwarding to keep the core fed with minimal bubbles and stalls. Dynamic feedback mechanisms from the system allow the core to regulate aggressiveness and proactively prevent system congestion. These fundamental concepts are what allow us to push width and depth of the machine while maintaining the short pipeline necessary for quick mispredict recovery. This diagram shows the basic pipeline of the Neoverse V2 core. It's an 8-wide machine with a 320 plus instruction out-of-order window. Now, for the next part of my talk, I'm going to be walking through the sections, colored sections individually, and I'm going to describe the improvements relative to our previous Neoverse V1 CPU. In each section, we're going to show the impact of these improvements in terms of performance on spec CPU integer 2017 benchmarks for a typical server system. Furthermore, the V2 is a ARM V9 implementation, so it includes technologies such as SVE, MTE, and all the other architectural features familiar to those who know ARM. Okay. The decoupled branch and fetch pipelines allow the branch predictor to run ahead, acting like a prefetcher. Combined with a low latency L2 cache, this enables us to use a relatively small 64K 4-way L1 instruction cache. The overall structure is similar to that of the V1, but the V2 reorganizes the branch target buffer, increasing the nano BTB by 10x and splitting the main BTB into 2 stages with 50% more total entries. Direction prediction is handled by a 2-stage Tage predictor, allowing 1-cycle prediction for common branches and a 2-cycle prediction for hard-to-predict branches. The history stored in the Tage is greatly increased by a factor of 3x. Indirect prefetchers now get their own dedicated predictor as opposed to overlaying on top of the other predictors. We double fetch and TLB bandwidth, and we increase the fetch queue and fill buffers to match the increased bandwidth. With this increase in fetch bandwidth, the micro-op cache is scaled down by half. This allows us to make for a more efficient and less power-hungry implementation. If you combine these changes in isolation, the fetch and branch improvements lead to a 2.9% gain in spec CPU 2017 integer. But as I'm going to show you later, real-world performance, we see a much larger gain. Decode. Decode takes up to 6 instructions from the instruction cache, feeds them through parallel decoders, and we handle simple instruction fusion cases as we're going through the decode process. Instructions that hit in the micro-op cache bypass decode at a higher width. You see 8 micro-ops coming in the top there, and they go straight into rename from there. At rename, the decoded instructions and those from the micro-op cache are combined, and we perform our standard register renaming. Improvements here over the V1 include an extra decoder lane to match the increased fetch bandwidth, and additional rename checkpointing, and improved rebuild handling following mispredicts. These improvements in isolation combine for an estimated 2.8% gain in CPU spec 2017 integer. Issue and execute. So just like the Neoverse V1, the V2 has multiple independent issue queues, some of which can actually issue two instructions at a time, the top 2 in the diagram. And these feed a dedicated set of ALUs that are organized by instruction types. So you see simple arithmetic operations, complex arithmetic operations, multi-cycle, vector, etc. Each one has its own issue queue. The issue queues here don't contain data. The register files are read after issue, and we combine the register file reads with forwarding data from the result cache and directly from the execution units themselves. This structure allows us to have very large issue queues, but it does have the downside of a large number of read ports into the register files itself. This is mitigated with port sharing and result caches with lazy write-back. Improvements here over the V1 include 2 additional single-cycle ALUs for a total of 6. That's a 50% increase. And at the same time, the issue queues feeding all of the execution units are all increased by varying amounts, pushing them to basically the limits of what the physical implementation can stand. At the same time, the more opportunity for instruction fusion and zero-cycle register-to-register and register-immediate move operations reduce issue queue, ALU, and register file pressure. These improvements contribute a combined 3.3% increase in spec CPU 2017 integer. On to load store. The load store unit consists of 2 load store pipelines and 1 load-only pipeline, accessing a fully associative TLB and a 64K 4-way set associative L1 cache. Store-to-load forwarding occurs at the L1 hit latency and covers most of the common cases of alignments and data types. Loads and stores execute fully out of order and with read-after-read structures and read-after-writes dealing with hazard detection and resolution. Improvements here over the V2 include a larger L1 TLB and a more sophisticated L1 cache replacement policy. Larger store buffer, larger RAR, and larger RAW structures help expose more ILP with fewer hazards and flushes. The larger store buffer does come at a cost of more compares against loads for read-after-write hazarding purposes, and these are often in the critical timing paths. But power and timing pressure here are mitigated by using VA hashing to perform that critical collision detection. We also see a large reduction in RAR-related flushes by tracking the lifetime of entries in the RAR through the lifetime of that in the L2 cache, not just the L1 cache, so that we can track writes from other coherent agents and only flush when absolutely necessary. So these changes in load store contribute a 3% to spec CPU 2017 integer. Prefetching. So the Neoverse V1 already had state-of-the-art prefetching using multiple engines training on L1 and L2 misses and prefetching into both L1 and L2 caches. Our prefetchers generally use virtual addresses to allow page crossing and allows them to act as TLB prefetchers as well. The prefetchers use dynamic feedback from the interconnect as well as accuracy and timeliness measurements inside the CPU to regulate their aggressiveness. The V2 builds on the V1 hardware by improving training, improving accuracy through better filtering and training operations, and making use of the program counter in more prefetchers for better correlation and better prevention of aliasing. New prefetching engines are also added. The L2 gains a global spatial memory streaming engine that increases the range of offsets of the prefetcher it can cover and it greatly improves over the older standard SMS engine. We add a sampling indirect prefetcher which handles pointer dereferencing scenarios. It's not data prediction, but it is learning patterns of data consumption as pointers for other loads. We also add a table walk prefetcher that enables prefetching of page table entries into the L2 cache. Now all of these added prefetchers and their aggressiveness can create congestion in the system, particularly at shared resources like the system level cache or DRAM. We provide differentiated QoS levels for demands and prefetches, and that allows us to have aggressive prefetching without hurting the loaded latency of demand requests. Dynamic prefetching, dynamic feedback regulates prefetcher aggressiveness to a sustainable level. Sorry. These changes combine for a 5.3% increase in spec integer. But more importantly, we see an 8.5% reduction in SLC misses at the same time. So we gain more performance with less DRAM traffic. Level 2 cache, my favorite. The Neoverse V1 has a private 1 meg 8-way set associative L2 cache that consists of 4 independent banks, each with a bandwidth of 64 bytes every other cycle, for an aggregate bandwidth of 128 bytes per cycle. It contains a large unified transaction queue that handles L2 misses, copybacks, writes, DVM operations, snoops, and internal hazard conditions, and it supports up to 96 concurrent outstanding transactions. The L2 cache is strictly inclusive of the L1 caches, so it acts as an efficient L1 snoop filter for the L1s and also enables hardware instruction cache coherency for the L1 instruction cache. The Neoverse V2 increases the L2 capacity to 2 meg, but it does so by retaining the same associativity and the same 10-cycle load-to-use latency of the V1's 1 megabyte cache. We enhance the replacement policy with additional RRIP states, and deadblock prediction is enhanced by tracking used once and used multiple lines separately. The AMBA CHI interconnect moves from version D to E and gains optimized store hit shared, cache maintenance, and memory zeroing transactions, as well as the ability to pass replacement hints from the CPU caches into the SLC. Overall, Spec 2017 integer doesn't see a huge gain in isolation from this, only 0.5%. But real workloads do, and we're going to see those gains very soon. Again, more significantly, here we're seeing that 8.2% reduction in DRAM traffic, which reduces pressure on DRAM and, more importantly, reduces system power. Okay, so if we go back to that pipeline picture and we combine all this data on this graph, you can see how they each contribute to the overall 13% Spec CPU 2017 integer score while reducing traffic by a total of 10.5%. But I see you guys out there looking, going, those numbers don't add up. That's more than 13%. And you're right, I can do basic math, so I saw that too. And the difference here is that the measurement methodology we use to turn these features on and off and run simulations is such that it creates interactions between each feature independently. And these interactions mean that the sum of the individual components is more than the realized gain. Okay, on to physical design. So a typical V1 implementation built with a 1 megabyte cache, and our targeted process for the V1 was 7 nanometers, came out at about 2.52 square millimeters. The V2 in 5 nanometer with a 2 megabyte cache comes in at almost exactly the same size, although in this floor plan the V2 is slightly narrower and a bit taller than the V1. The additional performance, the 13% spec int, does come at a small increase in power. We see about a 1.25 to 1 ratio between performance and power, in that a 1% increase in power in performance meant a 1.25 increase in performance in power. Sorry. Okay, the Neoverse V2 in a system can be combined with a wide variety of IP, either from ARM or from our partners, and from this you can compose a complete SoC. So the V2 is designed to be implemented along with a number of these IPs. The CMN700 coherent interconnect supports up to 512 megabytes of SLC, 256 cores per die, and multi-die configurations. The MMU700 provides SMMU capabilities for I/O devices. The NI, or non-coherent interconnect 700, provides non-coherent interconnect for I/O devices. GIC700 interrupt controller provides interrupt services for the system. And the NIC450 provides a non-coherent interconnect for debug, service processors, and general I/O devices. So my colleague Anitha is going to be discussing the composability of these types of systems later this afternoon, and I encourage you to see her talk. Next up, performance data. So on the following slides, the V1 and V2 comparisons are done using an emulated system. So we use hardware emulators, and there's equivalent system configurations consisting of 32 CPU cores with their largest possible L2 cache sizes, so 1 meg and 2 meg respectively, running at 3 gigahertz, connected to a 2 gigahertz 6x6 CMN700 system with 32 home nodes, 32 megabytes of system cache, and 4 DDR memory controllers. This basically represents 1/2 of what you would put on one die in a typical system. Spec CPU scores are estimated using reduced benchmarks, and those benchmarks are correlated against the full suite. And we utilize GCC 10 with standard compile options, no funny business, no special optimizations or anything. These are base scores. Starting with spec int. So on the left you see Spec CPU 2017 integer, single core. And it shows a 13% increase from the V1 to the V2. Some benchmarks do slightly better. X.264 is one of those. And here the gains are attributed to all the factors that I mentioned before. It's pretty uniform. On spec rate 2017 integer performance, the V2 shows a larger improvement of 17.3%. Here we get better scaling by the V2's larger L2 cache, the improved prefetchers, and more overall efficient use of system resources. Memcache D shows a similar 13 to 15% improvement at lower update rates, along with very strong scaling to more cores. Again, the V2 scaling slightly better. Higher update rates, the 5% and 25%, show a similar trend, but it does saturate due to limits by system performance. Nginx V2 shows a 20 to 32% uplift over the V1, depending on the usage of the server. Here again, we see the V2 scales better to higher thread counts due to its larger caches and more efficient prefetching. With the Percona MySQL server, the V2's branch prediction and hardware prefetcher improvements drive a 35 to 104% improvements, again scaling to higher thread counts better than the V1. The V2 sees a massive 80% reduction in branch mispredictions and a 70% reduction in unused prefetches. In machine learning, XGBoost, again driven by branch and fetch improvements along with a larger L2 cache, sees huge performance gains, 67 to 114% over the V1. ARM's partner NVIDIA built their Grace CPU superchip using 144 Neoverse V2 cores coupled with a high bandwidth mesh, coherency fabric, and LPDDR5X memory. NVIDIA is gracious enough to share this data collected on their hardware and that of our leading competitors. In terms of absolute performance, the graphs on the left, compared to Intel Sapphire Rapids in the dark gray and AMD's Genoa in the light gray, shows that the V2 has an edge on the competition, a slight edge. However, if you consider the real-world factor of a power-limited data center, the graphs on the right, the Neoverse-based Grace CPU superchip bests the workload throughput of AMD's Genoa by 70 to 150%, and Intel Sapphire Rapids by 140 to 200%. This data highlights ARM's position as the leader in power-efficient solutions for cloud, HPC, and AI and ML workloads. Special thanks for NVIDIA for sharing this and allowing us to share this with you. So in summary, the Neoverse V2 is designed from the ground up for cloud performance leadership with double-digit percentage performance gains across a wide variety of workloads, with targeted cloud workloads seeing 100% uplift. For HPC and AI ML applications, the Neoverse V2 sees large gains of up to 2x the performance of its predecessor and meets or beats the leading x86 CPUs in terms of raw performance, but beats them handily when real-world efficiency is considered. The Neoverse V2 is available for licensing today and is already in production in the NVIDIA Grace CPU superchip. Additional partner silicon is in bring-up and more implementations are expected. Thank you.
Questions? We'll start with the Slack channel while people line up.
Good morning. I've got a couple of Slack questions. So let's start with this one from Daniel Deng from Google. Your slides on instruction fetch mention the need to tolerate, use the word tolerate, a small L1 instruction cache of 64K bytes. Apple's M1, for example, has moved to 192K for their instruction cache. Can you talk about the choice of this small L1 instruction cache in V2?
Sure. Am I hot? Okay. Yeah, so you're right. The M1 does have 192 kilobyte instruction cache. We're finding that the 64K iCache is a sweet spot. The short latency L2, 10 cycle load to use, very large, and has replacement policy information to be able to maintain iCache lines. And the prefetching effect of the run-ahead branch predictor means that we don't need that large L1 cache. We get good performance with a 64K cache. It allows us to keep the latency low and the area cost low as well.
Okay, please state your name and affiliation, and then go ahead.
Hi, Chester Lamb, Chips and Cheese. On the slide where you laid out different pipeline components and the gain for each, do you arrive at each figure by taking a Neoverse 1 foundation, applying that change, and then looking at that gain in isolation?
Effectively, you can do it one of two ways. You can do it with a subtractive function, or you can do it with an addition function. So if you start with the V1 and you enable all those branch and fetch features, for instance, you'll get 1% gain. If you do the opposite and do V2 and subtract that and look at what did you lose, you get another one, right? We did the latter. It's a V1 plus the feature.
Okay, so you took V1 and added it. Got
Yeah.
it. Thanks.
Exactly.
George Kozma, Chips and Cheese. You guys were talking about the micro op cache and how having it ended up being more power efficient. Could you maybe explain that? Because in my head, if you're feeding out of the op cache, you can turn off your decoders. You don't need them on, saving power there.
Right. So the micro op cache by its nature is power hungry on its own. It's a very wide access, and it's accessed quite frequently. And really, in terms of real world benchmarks, the micro op cache only covers small loops. It can't cover these big scale workloads. So we found that we could reduce the size of the micro op cache, keep the same performance with the increase in throughput of the instruction fetch. And we actually saw very little power gain from that.
Thank you.
Let's take one more Slack, and then we'll go back.
So this one's from John Masters of Google. How much runway does the run-ahead give you before you need to go to the multi-branch run-ahead?
That's a good question. We're seeing some workloads that hit the limit of what we can do there. So we're working on newer improvements and better features to break that bottleneck. In general, though, I think we still have a little bit of leeway in terms of increasing IPC before we run into the fundamental limits there.
Okay, next.
Hello, my name is Mark Casas from the Barcelona Supercomputing Center. I was wondering about hardware prefetching. So you mentioned that when you prefetch virtual addresses, you allow the prefetcher to go across pages, across virtual pages. So my question is, do you always allow that, or is there any kind of mechanism to kind of throttle or control this prefetching across pages? Because we have seen... Sorry.
Okay, yeah, there's no specific don't cross pages function or setting or anything like that. We instead control the aggressiveness of prefetching by how far ahead do we get? How many cache lines ahead are we going? And we have various aggressiveness modes that are regulated by this dynamic feedback and accuracy and timeliness measurements, but nothing that forces us to stop at pages.
Thank you.
Any other?
Jeff Smith, Citadel Securities. Quick question about the CHI revision E zero write optimization you mentioned briefly. What is that?
What is it? Well, so when you're writing zeros, common memset, right? You're clearing memory on a page allocation, something like that. You're writing zeros. There's no need to set, and we do what's called streaming write detection, where we detect you're writing sequentially through memory. Stop allocating your L1 and L2 caches. You're just going to thrash them, right? And we start streaming these out to memory. So what you would normally do is send out a write transaction and then send a bunch of zeros with data. Instead, with Chi-E, we have a new request opcode that basically says, here's a write. Oh, and by the way, the data is going to be 0. So we don't send the data at all.
Okay,
so it shortens the protocol and eliminates DAT channel traffic. And that can be significant.
It's not on the read side. So you're compressing it right out, but if the system sees like, hey, I'm going to zero a cache line out, it still pulls the data into the L1, even knowing that it won't read it.
No, that's what the streaming behavior is all about, is you don't bring the line into the L1. So what you do, the first 4 lines go into the L1, the next 16K or so go into the L2, and then we say, hey, wait a minute, we're not actually have any locality with this. Let's start streaming these out to memory. So they don't allocate the CPU caches anymore.
Magnus, thank you very much for your talk.
Thank you. One more?
So a question from Amarveer Chana, Cambridge. What was the motivation behind moving from a 2 by 256-bit SIMD unit down to a 4 by 128? I figured you'd enjoy that one.
Yeah, I didn't mention that in the slides, but I knew I was going to get that question. So the V1 had 2 by 256 SVE units. The V2 has 4 by 128. So we still have the same throughput in terms of compute performance. The difference between the two, there's a couple of reasons. One is that, so vector code that's using them all for doing parallel computation, 2 by 256 will be a little more efficient because there will be fewer instructions. 4 by 128, though, becomes more useful when the SVE execution engines are being used for non-vector type workloads. When compilers start generating SVE code, you can use them more arbitrarily and at a finer granularity. The other one is it allows product configurability. We can easily scale down to a product that has 2 by 128 if we needed to, whereas with a 256-bit, that becomes more limiting.
Thank you. Let's thank our speaker. Yes. Okay, so now the second talk of the session, AMD. AMD comes from AMD. AMD Zen 4 core and 4th gen server, 9004 server. The speakers are Troester, I hope I said his name right, and Ravi Bhargava. They'll be jointly doing this presentation. Kai is a fellow silicon design engineer in the course group at AMD and is the Zen 4 lead architect. Kai has been with AMD since 2006, and prior to this role, he oversaw the development of decode unit of Zen 3 processor. He got his degrees from Technical University of Illinois in Germany. Ravi Bhargava is an AMD senior fellow and the lead performance architect for the Zen 4 processor family. And for almost 20 years at AMD, his performance work has spanned x86 cores, DRAM, Infinity Fabric. And he got his degree PhD in computer engineering from UT Austin and BSc from Duke University. So let's welcome Kai and Ravi.
Thank you for the introduction, and hello everyone. On behalf of the AMD teams that worked on the Zen 4 core and the Zen 4 based EPYC products, Ravi and I are presenting the next generation Zen 4 core and 4th generation AMD EPYC products. This presentation has two parts. I will cover the Zen 4 core, and in the second part, Ravi will be talking about the server products using this core. Zen 4 is based on the successful Zen 3 microarchitecture and continues to deliver power-efficient performance. 14% higher IPC, thanks to microarchitectural improvements. 16% higher frequency at same voltage, made possible by the new 5nm technology, but also frequency improvements beyond technology scaling. And up to 60% lower power when measured at the same performance. Another benefit of the new technology, but also due to many microarchitectural and physical design improvements. Let's talk about some major microarchitectural improvements in more detail, starting with the fetch engine. We improved branch prediction accuracy for power efficiency and performance by growing both the L1 and L2 BTBs. And we also grew and improved the conditional predictor. We also improved fetch bandwidth. The branch predictor can now predict up to 2 taken branches per cycle, and while there's still a limit of 1 taken branch per cycle for the op cache and instruction cache stage, being able to predict 2 branches per cycle allows the branch predictor to better compensate for existing stall cycles. We improved the dispatch bandwidth. Among the changes was support for 2 taken branches and an optimization of the integer scheduler assignment algorithm. Another power efficiency improvement was growing the op cache. And we grew it in 2 ways, 50% more ways, and the addition of one additional op per entry. Moving on to changes that we made in the execution engine. They are most out-of-order buffers grew to allow for the exploitation of more instruction-level parallelism. And we made some instruction latency improvements and changed the L1 data cache to be byte writable. The benefit of a byte-writable data cache is that it does not need to read the data cache when there's only a partial write, and in turn, that leaves more data cache bandwidth available for loads. And then we also grew the data side TLBs to support workloads with larger memory footprints. And we added new instructions, in particular a power-efficient AVX512 implementation, and I will have more detail on that later. For the cache hierarchy, the most significant change was doubling the L2 cache to 1 megabyte per core. Both the L2 and the L3 received larger misqueues to support more outstanding requests. The L3 cache capacity remained at 32 megabytes shared by 8 cores, and with our vCache technology, we have products that offer up to 96 megabytes of L3 shared by 8 cores. So I mentioned that we added AVX512 support to Zen 4, and the AVX512 extension provides a lot of benefits to software. And even without increasing the computational bandwidth, it can provide performance improvements. There's now per-lane masking, which allows for lower overhead code vectorization and twice the number of architectural registers for reduced register pressure for compilers. And not to mention that there is a code density benefit, since now one instruction can do up to twice the amount of work of an AVX2 instruction. And on Zen 4, the AVX512 support also comes with new instructions and data formats for accelerating machine learning applications, as well as new instructions for cryptography and improvements of the existing scatter and gather support. On Zen 4, AVX512 utilizes the existing 256 data path that we already had in our course since Zen 2. And without having a native 512-bit data path, most 512-bit operations execute in 2 consecutive cycles on the same execution pipe. While that means no per-clock throughput improvement, it allowed us to have a power-efficient AVX512 implementation with only minimal area growth. And even the physical register file, which can now hold 512-bit registers, had only minimal growth, since register file area is mostly limited by the width and number of access ports, and not so much the number of storage cells per entry. So aside from the architectural benefits of AVX512, and I already mentioned the masking and the increased number of registers, there's also a power benefit to AVX512 on Zen 4, especially with our implementation that utilizes a 256-bit data path. Compared to 256-bit AVX2, with AVX512, the core processes up to 50% less instructions for the same amount of work. And less instruction means less power for fetching, decoding, and out-of-order tracking. And the chart here on the left illustrates the relative power consumption of various functions within the core for an average compute-intensive workload between using AVX2 and using AVX512. And as you can see, while the power in the FP is not reduced, the power in the other functions is reduced. And in a power-constrained system, this reduction of power directly translates into increased effective frequency and thus performance. And we observed that. We observed a 17% increase in effective frequency when comparing an AVX2 and an AVX512-based HPL build. Both versions had almost identical computational efficiency, which means that the improvements did not come from AVX512's architectural advantages, but from the lower power consumption on the Zen 4 core. And Zen 4 also improves SMT uplift, which is a benefit from having increased pipeline bandwidth and deeper queues. While on Zen 3, we saw an estimated spec-int rate SMT uplift of 25%, for Zen 4, this uplift grew to 34%. And this particular data point is for running 2 copies on a single core with SMT enabled and disabled. But we also observe a significant SMT uplift improvements for larger core counts. Yes, it's true that SMT does not work for all applications, but SMT provides flexibility. With it, software can easily choose between high single-thread performance and high throughput performance. And for the high throughput demands of cloud computing, we created a compact version of Zen 4, which is used in our high core count Bhargava products. What we did to create Zen 4C is take the Zen 4 functional design, which keeps IPC and features identical between Zen 4 and Zen 4C. And especially the latter was important to us because it means that there are no software changes needed when transitioning from Zen 4 to Zen 4C. We targeted a design frequency optimized for cloud servers, and with that lower frequency, we were able to significantly reduce the area of the core. And that smaller area led to a tremendous increase in power efficiencies, allowing us to provide 33% more cores in the same power envelope at high frequency and IPC. Here's a comparison of the Zen 4 and Zen 4C core, including the L2 cache. The area was reduced by about 35%. And as you can see, this area reduction happened mostly in the floating point and the integer execution units, or execution parts of the core. And with that area reduction, and by reducing the L3 cache per core from 4 megabytes to just 2 megabytes, we were able to double the number of cores on a compute die. On the Zen 4C compute die, the 16 cores are organized as 2 clusters of 8 cores, and each cluster providing 60 megabytes of L3 to its cores. The size of the L2 cache did not change. Each Zen 4C core still has 1 megabyte of L2. And with that, I'm handing it over to my colleague Ravi.
All right. Thanks. So Kai just went over the Zen 4 and Zen 4C designs and how they can benefit server. So now I would like to discuss how we take those foundational elements and then build out our Zen 4 family of EPYC processors, shown here in the top right. So we have Genoa and Genoa X, which are our follow-ons, the 3rd gen Milan and Milan X. Then we have Bergamo and Siena, which are new, and I'll talk about those more in a bit. So how did we get here? You know, for AMD, this starts with our customers and their TCO, or total cost of ownership. AMD has a lot of great foundational technology and IPs that go into all products. But as you look closely at each customer's TCO equations, you'll see a lot of the same variables across these equations, but they'll be weighted or emphasized differently based on different customer needs. So these different needs and variables map well into this design vector table I have here. So here we're focusing on things like core and thread density, perf per watt, throughput, perf per core, and form factor. We design our products to be really strong across all of these dimensions, but as you keep pushing and pushing, it becomes, there's some natural tension as you try to optimize for all these vectors simultaneously. So this is what inspired us to look more into market-aware SoCs. The main strategic enabler for market-aware SoCs are our chiplets. So the rest of this talk is about our chiplets, how we've architected them to build out this family of processors, then how those processors target, 1 or 2 key elements of these design vectors. And the final output's going to be, a rich and differentiated set of products, all very high capability and performance and power optimized for the markets that they're targeted. So this is kind of a chiplet level overview of the processors. You can see one common element across all 4. That's the box in the middle, and that's our I/O die. And this is intentional. We want the same I/O die across all these products for platform level continuity. The I/O die interfaces off the chip to the DRAM, to PCIe devices, to our new CXL memory extensions, to the other socket through XGMI. It also has APIs and interfaces on the I/O die for things like power management. So once you kind of bring this whole system up once and get it configured and tuned how you want, doing these other systems comes at a much lower overhead, both for us and for our partners. So if the I/O die is the same, then what's different? Of course, we have two different core chiplets. We have the Zen 4 core chiplets in Genoa, the Zen 4C core chiplets in Bergamo. And then the Zen 4 core chiplets can be further differentiated by stacking on 3D V cache, which is more L3 cache, and that's Genoa X. And beyond these 4 chiplets, 4th gen EPYC has a rich new set of flexibility. And the flexibility is not just about new configurability, which it has, but making sure when we configure in these high leverage configurations that we have high performance and power efficiency at the same time. So let me walk through each of these processors now. Start with Genoa. This is our flagship processor. It's designed for high performance and balanced computing, so it's meant to be really strong across all of the design vectors. We think this is just a great product for all types of customers, all types of markets. You can kind of see this in the chart here where we are comparing our previous generation 64-core Milan with Zen 3, a 60-core Sapphire Rapids, and then a 96-core Genoa. And you can see throughput improvements here of 70, 80, 90% over a variety of really interesting server workloads. So if we use this kind of Zen 4 Genoa with 12 channels of DDR5 as our baseline, let me talk about some of these other members of the family. Bergamo is targeting high core thread density, high throughput per socket, but at the same time, we want to reduce or increase performance per watt and reduce power. So the main enabler for this is our Zen 4C chiplet. So you can now see 8 of these Zen 4C chiplets. Each one has 16 cores. So now we have 128 cores versus 96 on Genoa. So it's a 33% increase in core count. But it's not just about stamping down more cores, right? We want to make sure that the performance and power are scaling efficiently as well. So one area we target in the I/O die to enable Bergamo level of scaling is our coherence network. So there's these Zen 4C complexes, and they talk to each other through the Infinity Fabric. And from a coherence perspective, they're using probes. So that's one area we tried to accelerate through techniques like probe compression, which is taking multiple probes, packing them together through different stages of the pipe. Probe reduction, so these will be microarchitecture techniques of when do we decide to send a probe and how many. And then higher probe bandwidth, but of course you don't want to do that everywhere because that's not power efficient. So we find the pinch points, widen those, and again keep these probes zipping through the system. And this helps us scale things like DRAM bandwidth and intercore communications for the extra cores that we have on this processor. Beyond that, it's a really natural transition, especially for the I/O die, to go from a Zen 4 chiplet to a Zen 4C chiplet. The interfaces are exactly the same. All the power management across the chiplets remains the same for all 4 of these products. And so this kind of all culminates for Bergamo in something like this graph on the bottom. So this is a 60-core Sapphire Rapids and 128 of our Zen 4C cores of Bergamo. And the metric here is a performance per watt metric for spec power. So you can see with about twice as many cores, we're getting about twice as much performance per watt. So this is the type of power efficient and performance efficient scaling that Bergamo enables. So Genoa X is, aggressively going after performance per core. And the main lever for this is the 3D V cache. So like Kai said, we start with an 8-core, 32 meg of L3 core chiplet, and that's already a lot of L3 cache for 8 cores. Then when we stack on the 3D V cache chiplet, you get 96 megabytes of cache. That's just humongous. And for workloads that are amenable, and of course, not all workloads are amenable, but for the ones that are, with like big iCache footprints, really big data working sets, they can see a step function in performance with the 3D V cache. So the I/O die was also modified and enhanced with Genoa X in mind, and here we targeted the probe filter. So this is a feature. Its job is to track all the cache lines that are cached in the system and their coherent state and manage that. And if you can't track all the cache lines, then you can't cache them, and your L2, L3 caches become less efficient. So you could, and with Genoa X, what have we done? We've tripled the amount of cache versus Genoa. It's 50% more cache versus Milan. So we could just throw more entries at the probe filter, but that would not be power efficient or area efficient for the other products, right? So what we focused on was enhancing the capabilities of the probe filter entries, as well as using the entries that we have more efficiently. And so these combined improvements lead to a more robust probe filter, which means fewer edge cases and corner cases, things like hotspotting, which leads to a better L3 efficiency and higher V-cache uplifts. There's an example of that in this chart. So this chart is now 32-core Sapphire Rapids and a 32-core Genoa X. So same core count to kind of show performance per core. And there's 4 different suites here, and you can see some of the subcomponents within the suites are improving by up to 2x, again at the same core count, and this is driven by the 3D V-cache. All right, Sienna. So Sienna is the newest member of the family. In fact, it's so new it has not launched yet, so I can't quite talk about this one as much as the others, but I can say that the Sienna platform here is targeted for performance per watt and for a smaller and power efficient form factor. And I say smaller, but it's still up to 64 of our high performance cores with SMT 128 threads. The 6 DRAM channels all go up to D5 4800. And in general, you have all the features and capabilities, bells and whistles of all the other server products in Sienna. So we think this will be just a great product for certain markets and certain customers. You can imagine maybe a balanced computing system where there's just a certain fixed amount of system budget for the CPUs, right? But when the CPUs are needed, you want them to be high capability, high performance, high power efficiency, and these are areas where Sienna can excel. All right, so I just talked about the 4 different processors, so I'm going to change pace a little bit here, and this is talking about a flexibility option that applies to all 4 of the families. So this picture here is kind of a zoom in of the I/O die and the Infinity Fabric, but we can just concentrate on those dark green boxes at the top and bottom. Those are the core chiplets, or we call them CCDs sometimes. Those little green arrows, sorry you can barely see them, but those are the GMI links. Those are our high speed, high bandwidth interfaces between the core chiplet and the I/O die. So the 2 configurations at top is something we've been doing for multiple generations, where we have 1 GMI link per core chiplet. And this is what's been enabling the large core count improvements over time, yet at a great power efficiency. What's new is on the bottom. So these 2 configurations are GMI 3 wide. So now we can take 2 GMI links for a single core chiplet. So whether it's a Zen 4 or a Zen 4C chiplet. So 2 GMI links means twice as much bandwidth into the Infinity Fabric. And what this enables is for a smaller number of core chiplets to max out the DRAM bandwidth in the system. And this gives us more configuration options to fine-tune our products for perf per watt, perf per core, and or form factor. Okay, the last thing I'll talk about here is memory technology. And again, this applies across all 4 members of the family. So memory is obviously important, but there's 2 things our partners have focused us on over this kind of Zen 4 epic journey. On the DDR5 side, of course, everybody wants high efficiency DRAM across every config you can throw at it, but the config with the focus has been single rank. So part of the reason is in previous generation with DDR4 and legacy systems, the single rank versus dual rank bandwidths were like tens of % off from each other, where single rank was worse. So this kind of took single rank off the table as a reasonable system config option. But with DDR5 and 4th gen EPYC, we have this gap down to about 5%. So now single rank is now viable for system builds, and it gives you more options depending on your DRAM footprint needs, perf per watt needs, and form factor. Kind of the other end of the spectrum is when you just want a lot of memory. And for this, we have CXL memory expansion. So CXL is a different interface for memory. And for AMD, we're supporting CXL 1.1. Our partners go, yeah, that's great. But there's some 2.0 features that would be really nice to help us build out CXL ecosystems in the Zen 4 EPYC timeframe. And so we've added those, and now we're co-optimizing and building out these initial CXL memory expansion ecosystems, and laying the groundwork again for more options for flexibility, form factor, and perf per watt. All right, I'm going to wrap up. Kai talked about Zen 4, how it keeps pushing the boundaries on single thread performance and SMT uplifts. He talked about the really cool power efficient AVX 512 implementation. We both talked about Zen 4C, which is optimized for power efficiency and area, but without having to compromise on IPC, ISA, and other functionality. And finally, I just went over with you, how we took Zen 4, Zen 4C, our Vcache chiplets, our IO-die chiplets, and built out this differentiated set of processors targeting specific customer needs and design vectors. And we end up with a series of products that are power and performance efficient for the markets in which they're targeted. All right, and I'd like to thank all the AMD team, our PR, legal, and marketing teams, as well as our senior technical leaders, a lot of whom are here today, and then of course our hundreds of design engineers from Zen 4 and all 4 of these products who really put all the magic into them. Thank you.
Okay, right on time. So, time for questions again. Like always, we'll start with the Slack.
Certainly. There are a very large number of questions in the Slack channel, so we won't get through them all. If you guys can maybe follow up after the talk on Slack, that would be great. A collection of them are about the differences between Zen 4C and Zen 4. These questions come from folks at Google and NVIDIA and Oracle Labs. So kind of the overall question is Zen 4C sort of a parameterized instance of Zen 4? Are there more fundamental differences? And then, does Zen 4C have dual MAC pipes? Do the Zen 4C chiplet cores still have multi-threading? So it's all sort of about some of the differences.
Right, so let me address that question. It's not parameterized because it's the same functional design if you think of parameter as affecting the functional design. So, yeah, it's just the same core, but smaller because it has a lower frequency target, so it's more power efficient.
That answers the question of how did you fit it in such a smaller area. So it's a trade-off in performance.
It's giving up on the top end frequency, which is not as important for cloud computing, and then it gets smaller.
That answers the questions. Then thank you.
Sure.
Next question. Go ahead.
Hi, Charlie Demergent from Semi-Accurate. On Rome, each CCD was 2 logical units that didn't talk directly yet to go through the I/O die. That was changed in Milan, in Milan, to a single logical unit of 8 cores. But with Zen 4C and Bergamo, you went back to the 2 logical units that can't directly talk. Why?
Yeah, I got it. So yeah, I mean the logical units you're talking about are core complexes, and the chiplets you're talking about are kind of the physical layout of these kind of more logical abstractions of our core units. And so kind of that best mapping is really just going to be design specific, right? So how many cores, what can we fit into a core chiplet? So, there's kind of the same design at the logical abstraction level. We just have different physical trade-offs we can make with each project as we change the design of them.
But why leave the latency to have the 2 logical CCXs talk on a CCD?
Yeah, I think you're asking about the latency to talk. So that is part of the architecture. Again, like I said, the logical abstractions are still the same, and so their interfaces still remain the same.
Okay. Next question.
George Kozman, Chips and Cheese. So I was interested in that you guys increased your micro-op cache, which you guys say decreases power and latency. Yet the previous presenter showed having the op cache. So where do you guys see that power decrease in the increase of the op cache?
So let me address that. So the previous presenter was talking about instruction set architecture, and there's a different balance there between the energy needed to decode instructions, kind of in terms of what you save, and it's also a different code density balance, and so as a result, we likely end up at different optimization points.
So it's an ISA difference then. Essentially, the balance point is different for ARM versus x86 in this case.
Correct. I mean, we also are focused on optimizing spec-in performance, so we're actually working to the same benchmark. So I see it as natural, to come up with different optimization points. Yeah.
Okay, thank you.
Okay, let's take one more here and then we'll go to Slack.
Jeff Smith, Civil Securities, and I have another kind of wedge question. So for AVX512, you guys opted to do dual cycle issue 256-bit data path, and you say that there's, in your estimation or your opinion, there's minimal overhead, or it wasn't too heavy a cost for the register file size increase and so forth. On the other hand, we have AVX 10, I guess, announced, which is seemingly trying to convert back on 256. So when you guys were designing your approach for Zen 4, I'm sure you had similar ideas. You could have taken another direction. So what's your justification for what you did versus what maybe alternate solutions might be pursuing in the future?
So when we designed Zen 4, AVX 10 was not yet announced. AVX 512 was just announced, and we saw the opportunity that it would provide for software. Yes, recently AVX 10 was announced, and it approaches the problem different. Unfortunately, it does require different code paths for processors that have 256-bit and 512-bit native data paths. So.
But you did not see the tipping point at quite the same point as maybe the AVX 10 creators did, I guess, is the answer.
Well, also when we created AVX 512, Zen 4, AVX 512 was just new, and we wouldn't know how the adoption of it in the market would be. So it didn't make sense to kind of spend the extra area on creating these large data paths.
Okay.
Thank you guys very much.
You guys can talk offline. Okay, let's do quick 1-minute question.
Yeah, Chester Lamb from Chips and Cheese. When you guys did your AVX 512 stuff, you expanded the register file to increase reordering capacity for those 512-bit operations. Yet for 512-bit stores, that reordering capacity is not increased, meaning that it's half of what you get for 256-bit operations. So could you explain that?
Correct, because we implemented the stores as two 256-bit store operations, whereas the load is implemented as one 512-bit kind of double pumped or two consecutive load operation, and that's probably why you see differences in the capacity, because you're talking about the store capacity, right?
Yeah, why increase the reordering capacity for general AVX 512 like bytes to registers, but not for bytes to memory?
Maybe we can take it offline.
Yeah, let's take it offline. I just want to understand that better, make sure I have a good answer.
And sorry, we are 1 minute over, so you can talk to him offline. You guys are still here, right? Yes.
Yes.
Thank you. Thank you, speakers. Okay, so for last but not the least, the third talk of the session comes from Ventana, and Greg Favor is our speaker. He's the co-founder and CTO of the company. He has been architecting and designing microprocessors for 39 years, both at startups and large companies across many architectures. PowerPC, x86, ARM V8, RISC-V, just name it. And Greg is also currently chair of RISC-V Privileged Instruction Privileged Architecture ISA Committee, vice chair of RISC-V Technical Steering Committee, and is actively involved in a number of RISC-V task groups. So let's welcome Greg.
Yeah, thank you. Well, hi everyone. Is my good?
Yes.
Okay. Yeah, hi, everyone. Today, I'm going to be talking about our first generation Veyron V1 processor, which is a data center class processor based on the RISC-V architecture. This was announced last year, as well as completed last year. So as you might then expect, we are well into the development of our second generation V2 design as well. Currently, it's already up and running, Linux, a wide variety of applications. One of a number of big vectors that is pushing is a large increase in IPC. And we'll be talking about that at the RISC-V Summit in November. For today, I'm going to talk about the microarchitecture of V1. After a couple of initial slides, I'll then get into a bit of an overview, show the pipeline, various pipeline diagrams, and then come back around and talk about some of the atypical microarchitectural choices we made in the interest of not just simply getting high performance, but also doing it in a more power efficient way. Okay, first, as far as target markets. It starts with data center, but there's really a common thread across all these markets where there's a need going forward for very high performance, but also in a very power efficient way. And in the case of data center, you have a power budget, a TDP limit, and how much performance, how many cores can you pack into that power limit and maximize the performance you can get. In the case of automotive, the next generation architectures are essentially becoming not just one, but multiple servers on wheels. In the case of the edge, again, sort of data center class systems, smaller core counts, power is also a big deal there. And then when you go to client, smartphones and other mobile devices, that probably one of the biggest challenges as a lot of client people move to RISC-V architecture is the high-performance CPU, where you, again, need the same kind of very high performance, but in a very power-efficient way. Okay, let's see. Before I get into the actual microarchitecture overview, this shows a couple of things. First, that what we develop is not just high-performance RISC-V CPU cores, but what we call a compute cluster, which is cores, full three-level cache hierarchy, multiple cores in a cluster tied together by a coherent fabric. We also develop and provide to our customers other key IPs such as RISC-V IOMU and the RISC-V Advanced Interrupt Architecture. We then offer what we develop in two forms. To some customers, IP still makes a lot of sense. There's a growing number of our customers where the economics, the technical flexibility, and a number of other advantages leads them to find chiplets very attractive. And that just shows one example of an I/O hub with the I/O and DDR with various chiplets, not solely Ventana chiplets, but possibly other chiplets, customer-specific and or maybe domain-specific or AI accelerators. And in fact, later, not today, but later time, we'll be talking some about what work we're doing in terms of domain-specific acceleration as well. Okay, just from the big picture, what we call a compute cluster. Each core is a true high-performance Intel AMD ARM class CPU. An aggressive full out-of-order design, and along with a substantial L1, L2, and L3 cache hierarchy, private L1 and L2 to each core. Within a cluster of up to 16 cores in our first generation, there is then a cluster-level shared L3 cache as well that can be up to 48 megabytes. So in aggregate, about 64 megabytes of cache between L2 and L3 within a cluster. This is all tied together with a coherent fabric of our own development as well that is based on a CHI protocol, similar to that, but significantly enhanced for more performance. And in chiplet form, we've also developed a full, complete die-to-die solution. Not only file layer, but link layer, transaction layer. Half goes on our chiplets, half we provide to our customers to incorporate into their hub, design into other chiplets they might want to do. And this is a server class product, including, for example, full support for virtualization on the CPU, I/O, and interrupt side. RAS, we protect everything. Basically, it's an enterprise class RAS story, including data poisoning and so on. Okay, Now I'm going to, after this slide, get into an overview of the microarchitecture, and then I'll come back around, like I said, to some of the interesting things or choices that we have made. But at an ISA or architecture level, we're of course implementing 64-bit architecture, and we start with the sort of base set of RV64 GC extensions, and we implement a whole host of additional architecture extensions on top of that that are relevant to sort of Linux-based systems, server-class high-performance system designs. Most notable among that is the hypervisor extension, as well as the new advanced interrupt architecture. As one would expect, we also support large virtual and physical addressing, and then performance counters, performance analysis capabilities, a whole host of things. Okay, this will start with an overview. Like I said, this is a superscalar aggressive out-of-order design. And there's a lot of you might say innovations in our microarchitecture, sort of atypical choices that we've made, and then take some innovation to make those things work and work well to give us the performance and the power efficiency. Another key thing that we set out when we started developing this microarchitecture is to not depend on custom design at all. Give us a standard cell library, give us a RAM compiler, we're good to go, and we architected with that constraint in mind to get the high performance still. That gives us a very portable design. Starting from the front end of the design, it is what has become more common nowadays, a decoupled predict fetch architecture. We have a lot of predict and fetch bandwidth. That starts with having both a large BTB and large branch predictors, and then we can fetch up to 64 bytes per cycle, decode up to 8 instructions per cycle. I'll talk a little bit more in a bit about supporting both the 16 as well as 32-bit RISC-V instruction sets, so we'll decompress the compressed 60-bit instructions on the fly. We also look for common code idioms where we can fuse RISC-V instructions together into single micro-ops. And that goes past what you see in other architectures where usually it's like compare and branch type fusions. This is, that's already taken care of by the RISC-V ISA as a single instruction. So there's a lot of other common types of idioms that will fuse. And from the decode pipe onwards, everything is in terms of ops. Some fused, some not fused, decode, dispatch, issue, execution, etc. It's all in those terms. So there's a certain kind of multiplier effect for thereon stemming from fusion. Okay, looking at the back end. First, which is one of our atypical choices, is we don't brute force having a lot of dedicated execution units, register units, branch units, load units, store data, store address units, and so on. We have 4 symmetric integer execution pipes that can execute any mix of register, load, store, branches per cycle. One cycle, it can be 4 loads. The next cycle, it's maybe 1 reg, 2 stores, and a branch. Next cycle, 4 branches. Any mix, with only a very small number of exceptions, such as fully pipelined integer multiply, and then of course integer divides, pop count, CMO, and so on. They are handled or executed via a separate 5th shared execution unit. In front of all this is our large schedulers with an aggregate capacity of 128 entries. So a very large scheduling window for us to go find ILP. Now at the same time, this is all in recognition of the fact that actual ILP on applications, some you're under a 1, some are 1 to 2, maybe on good days 2 to 3. We have a set of these 4 execution pipes that we make very efficient use of instead of underutilizing a much larger set of dedicated units. That saves area, power, a number of advantages, as well as helping timing in some regards. On top of all that, there's instructions that are loading constants into registers, and those will recognize and we will sort of perform them at dispatch time. So effectively they have 0 cycle execution latency, and they don't consume any back-end resources from the scheduler onwards, or schedulers onwards. Scalar floating point, architecturally separate register file. We have separate schedulers and pipelines for scalar floating point. And then in terms of the cache and TLB hierarchy, we have very consciously architected for both large code and data working sets, and for low latency. And one of the first typical things we've done is we actually have a split IND cache hierarchy. On the instruction side, it's a large single-level half megabyte instruction cache with all the benefits of both of high hit rate. At the same time, through some innovations, we can access that with very low latency, and I'll show that in the pipeline diagrams. We do have an L0 cache, which is really more just for power efficiency purposes, or in other words, power saving purposes. On the data side, we do have a two-level cache hierarchy, a good-sized L1 data cache, backed up through inclusion with an L2 half megabyte data cache. By separating the IND, that enables us, among other things, to optimize each of those very differently for more power efficiency, for much lower latency, which translates into performance as well. We also then have a separate instruction and data TLBs, very large. The 3K pluses because of some additional prefetching and clustering capabilities that we also support in our TLBs. Okay, just to give you a look at the execution pipelines. Let me start with the blue one, towards the upper left, which is our predict pipe. And really, the PR1, PR2 are the main pipe stages, which then feeds into the fetch pipe. That is a decoupled 5-foot interface, but potentially can feed straight into the fetch pipe, which most of the time operates as just a two-stage pipe, where we can both do address translation through those large TLBs in parallel with tag lookups in that large single-level iCache, as well as data access from that large iCache, all in two pipe stages. It's the rare time that we have to unfold the pipe and do that sequentially. Almost always, we're in a folded situation. That then feeds into the decode pipe. And I'll touch more on that in terms of some of the fusion and decompression and other things as well, on top of being able to decode up to 8 instructions per cycle. And then the back end, again, is your integer execution. Most, all branch, most red jobs are all single cycle, except things like, say, a folding pipeline integer multiply, careless multiply, things like that, which are more than one cycle. The load store pipes, which again are branching off of the same schedulers and so on, is 4-cycle load use latency, fairly common nowadays. The scalar floating point pipes, as I mentioned earlier, separate architectural register files, separate schedulers, separate execution pipes, and then there's various commit and retire pipes sort of at the end of the day. One common metric is what is your branch miss prediction penalty? If you count from IX1 in the integer execution pipe, which overlaps with RPS, the beginning of restarting the front end while we flush out younger ops, we update and retrain branch predictors and various other things, and then restart the predict and fetch pipes. That if you count properly, that is a 15-cycle branch miss prediction penalty. That comes down significantly in our second generation design. And in both cases, that is including the latencies for accessing large BTBs, large predictors, TLBs, caches. We don't mess around with two-level hierarchies and all that. So we actually get an awful lot done in that amount of time. And like I said, we'll be even still cutting that number down in our second generation. Okay, now let me come back around to touch on some of the other sort of atypical design choices. One I already touched on was 4 symmetric integer execution pipes. So in terms of predicting the fetch stream, we can, any given prediction is of a sequential run of instructions up to 64 bytes long. We have a large single level BTB, as well as a similarly large collection of conditional branch predictors, indirect branch predictors, return predictors, etc. It's all fully pipelined, and that is driven by a next lookup predictor that enables us to be predicting once, the next 64, up to 64 byte run of instructions every cycle. That next lookup predictor is fast, it's small, obviously occasionally gets it wrong. That's just a 3-cycle hiccup. Given how much fetch bandwidth and both predict bandwidth and fetch bandwidth that we have, that more than covers the occasional next lookup predictor hiccups. On the instruction side, as I mentioned earlier, that is separate from the data side, and half megabyte IL2, and partially, that helps in terms of a lot of workloads with large code and data footprints to cut down the kind of ugly contentions that can happen between code and data. But foremost, really the motivation is to be able to separately optimize the instruction side and the data side for latency and for power. And as I mentioned already, this is fully pipelined, 2-cycle latency for doing translation, tag, data, all in parallel. If we go now to the decode stages, up front, at the beginning of the pipeline, decode pipeline, we decompress the 16-bit C extension instructions into their equivalent 32-bit instructions. We also do a quick pre-decode of instruction length, which is very simple to do in RISC-V architecture. And we'll identify the next 8 instruction boundaries that we're going to be looking at to feed into our decoders. We also look for instruction pair fusion opportunities as well. And we resolve all that early in the pipe, extract out instruction bytes, and then on down the pipe we go, converting into ops and renaming and dispatching those. On the load store unit, also as I kind of mentioned earlier or implied earlier, we can do any mix of up to 4 loads and or stores per cycle. With separate data cache hierarchy, so that we can really minimize the L1 miss L2 hit latency, as well as even the latency when you miss an L2 and have to get on out into the system. The L1 cache, 64 bytes, it is a fully virtual cache. I already mentioned 4-cycle load use. And being a fully virtual cache, there is a large single-level data TLB that only gets accessed on cache misses on your way out to the data L2 cache. Key things about being a fully virtual cache is that this is completely software transparent, no dependencies on software or any kind of optimizations or anything. And so conversely, we handle all synonym issues in hardware. In fact, we even allow multiple read-only synonyms to be co-resident even in the L1 cache. It's only when you then go modify one that you need to clean up the others. Also, fully in hardware, we maintain cache coherency based on inclusion with respect to DL2. And lastly, we also in hardware maintain full TLB consistency, meaning that software understands when it needs to do TLB and validate instructions, and we take it from there and we'll clean up the data cache as need be. The L2 cache is half megabyte, like I mentioned earlier, fully pipelined, 64-byte wide data paths, so we can go out to L2, come back, including going through that data TLB and so on, in less latency on the order of 11 to 12 cycles compared to other people who are already up, heading towards like 14, 15, etc. cycles for L1 miss, L2 hit latency. So again, a very optimized path. And then, of course, we have a variety of advanced data prefetchers, both next line, sequential, strided, and even multi-stride patterns can be recognized. And we do this in a staged manner. We will prefetch sort of one step ahead, or one line ahead, if you will, from L2 into L1. But then we'll be prefetching much further ahead, 5, 10, 20 accesses ahead, line accesses ahead, pulling from L3 inner DRAM into L2 as sort of a staging area. So it kind of manages the kind of pollution aspects, while at the same time, these are all confidence-based predictors that have a very low amount of useless prefetching going on. Okay, now let's pop up to the cluster level. In our first generation, we support up to 16 cores. That grows in our second generation, along with the big IPC increases. And as I mentioned, private L1 and L2 caches within each core, essentially a megabyte of cache within each core. And then at the cluster level is a non-inclusive shared L3 cache. It's not simply exclusive in that there's a variety of optimizations for various code and data sharing scenarios. And of course, some relatively sophisticated replacement policies on the L3. The L3 is also sliced, so as you vary core count, you also vary the corresponding number of L3 slices. So in a 16-core cluster, You also have 16 slices of L3, address interleaved. And as you'll see in a little bit, that gives kind of a nice physical building block as well. Just to finish off at the cluster level, we have a standard CHI interface coming out of the cluster. We want to make life easy for our customers to integrate into their SoCs, whether in IP form or chiplet form. And as I mentioned, we have an enhanced CHI-like protocol inside. And then in terms of the physical topology, it's what some would call a racetrack interconnect topology. We looked at the various kind of topologies for scaling up to 16 cores. This was the most optimal in terms of latency. It runs at full, at like 2.5 gigahertz, near to full processor speed, lots of bandwidth, and very short latency traversing that interconnect. Okay, this shows in terms of socket level performance. In a server kind of situation, you have a set TDP of, say, 280 watts. This shows you a comparative example of what you can achieve, last year with us and others. The key point is that, we have cores that are not just high performance, but also very power efficient, so that you can get a lot more performance packed into that TDP limit. And again, without having to sort of compromise on the performance to get your power efficiency. And one other note is, that's one of the two key things about what we do. The other is a chiplet-based architecture, which is very appealing to a lot of our customers in both not only economic but lots of other technical and respects as well. Last slide. This will give you a little more of a physical feel. This shows a 16-core cluster. You can see what each core, each L3 slice, and each slice of the fabric, the coherent fabric, what they each look like. And then you can see how it's arrayed in a very nice, regular building block fashion with 8 cores along the top, another 8 along the bottom. As you go vertically inwards, you have your 8 plus 8 L3 slices. And then you have your coherent fabric slices across the center from left to right. And then off on the far right is a very little system bridge for bridging into the rest of an SoC. And whether there's a dotted-eye interconnect or not, that's all transparent to the cluster and transparent to what lies on the other side. Our first generation was taped out in TSMC 5 nanometer. And I already mentioned about being a very highly portable design, as well as some of the configuration. That gives you a sense of the performance. This spec in 2017 rate equal 1. Depending on product SKUs, it's around like a 5 to 6 spec score. And with that type of total cluster power, when you also look at other kind of operating points to get a sense of the per core power, that you start from something that's capable of very high frequency and DVFS and also burning some power. As you come back down that curve, you get down quite readily to under a watt per core while still operating at 2.4 gigahertz. And of course, in all this, there's a lot of active turbo power management features, temp sensors, or continually estimating the active power that we're burning within each core, within the non-core parts of the cluster, and so on. And that is it. Thank you.
Okay, question time. And in some of you probably noticed company confidential. None of this was confidential.
Yes.
We'll take care of that.
By the way, I forgot to mention that, but yes, that will be removed by tonight.
Yes.
So that was an oversight.
Good. Hi, thank you for the presentation.
Wait, let's start with the Slack first.
Oh.
So, Greg, to start out, great talk. I'm down here. Hey, nice to see you. You have a vast number of questions in the Slack channel, so if you can maybe go answer them afterwards. I'm not going to get to very many here. Manu Gulati from Qualcomm. He asked a question that a lot of people are interested in. I know this answer is going to be straightforward for you. In the pipeline description, it seems there are 8 decoded instructions per cycle, but only 4 execution units. So what's going on with that? We typically see more execution slots.
Right, yeah.
Go for it.
Well, secondarily, there's an element of, especially like that for advanced risk predict, be able to get a lot of stuff into the scheduler so you can start looking for ILP. From an execution unit perspective, you have the 4 integer execution pipes, 2 scalar floating point pipes, as well as sort of that pipe for dealing with content loads into registers. So depending how you want to view it, it's more than 4, but in a sense, the back end is really based on, okay, well, how much ILP is there? And having more units isn't necessarily buying you much. But through the symmetry, we have the flexibility to, this cycle, oh, we want to do 4 loads. Next cycle, 4 register operations. Yeah, I'll stop with that.
Good.
Hi, this is Tao. Yeah, very interesting topic. So I have 2 questions. First one is about the vectorization. So you didn't mention any about the RISC-V vectorization. Do you have any plan to support that?
Short answer, yes. A little more context. RVV, which is a vector length agnostic vector architecture, was completed and ratified last year. But kind of later in the game for us doing our first generation, but at the same time, we very consciously left out vector unit. A lot of our early customers weren't necessarily interested in that and would rather not pay the costs and area power, et cetera, of having a vector unit in the design. So a lot of our early customers were actually quite happy without the burden or cost of vector unit. Our second generation, conversely, has a very beefy vector implementation, both wide, multiple pipes, very high performance.
Okay, thanks. The second question is quick. So I'm wondering if there are any third-party IP die to interoperate with your CPU cluster die?
Yes, that is a work in progress as that is happening. We have our first hub partner that is the first hub that works with our first silicon together, and we're working through with other companies to develop other, if you will, standard hub offerings. Some customers will want to develop their own hub optimized to their needs, and we'll support that with appropriate IPs and die-to-die and so on. But there's others that really do want, they just want to leverage standard hub offerings. There's not going to be one hub that's the be-all, end-all. Some that are more optimized maybe for server applications, some more for automotive, et cetera. So we're talking with various companies to work towards having a variety of hubs that we can plug into.
Thank you.
So related to this integration, UCIe plans?
Oh yes, yes. So. You go back before last year, UCI was not even announced yet. We were part of the group that helped develop the ODSA BOW standard, which is a parallel style interface like UCIe. And so that is what's implemented in our first generation chiplets, is BOW-based PHY, as well as our die-to-die controller. We were aware of UCI coming on even before it got publicly announced, and we are moving our controller on top of UCIe raw streaming mode as we speak. So yes, our second generation will be based on UCIe. But again, key point is it's UCIe raw streaming mode because we don't want to be going through protocol translations into CXL, things like that. We take your standard popular AMBA bus standards like CHI and AXI. We natively, transparently transport those across. Pick your PHY. Yesterday it was BOW. Tomorrow it's UCIe.
Okay, great. Oh, yes,
yeah, sorry. Ian Cutler, Small More. Thanks, Greg, for the talk. Much appreciated. 2 simple questions, if I may. First, you said you're doing first tape outs of silicon. So does that mean all the benchmark numbers and power numbers you provided were based on simulation and not actual silicon?
Okay. So we tend to emphasize getting our design into first an emulator platform and then into FPGA platforms, ASAP, essentially, instead of spending more time messing around with performance models and all the obvious inaccuracies and et cetera. And so everything we do at this point is based on running the real design in emulator and FPGA platforms.
Yep, and the other quick question is, interesting that you're doing this sort of symmetrical integer pipelines, this sort of one-to-one, to-one-to-one, everything. What sort of workload traces...
I think what you're that... Can you start the question again?
Yeah, so interesting that you're doing these 4 symmetrical integer pipes. What sort of workload traces were you running to come to the conclusion that that was the ideal balance?
If I heard the first part, that was about the symmetric pipes?
Yes.
Yes. I mean, certainly it starts with the spec benchmarks. there's a fair bit of variety there. You get into other workloads. Some can be higher IPC. There's a lot of cloud workloads that are lower IPC. And we sort of take an approach of getting a variety of data points, and you don't make decisions solely based on those data points, but you recognize that there's other workloads with different characteristics. But essentially, a variety of workloads starting with spec as well as some other of your typical kind of cloud benchmarks.
Were any of those traces customer driven?
Well, sorry?
Were any of those traces customer driven?
For our first generation, no.
Okay.
For our second generation, yes.
Perfect.
Okay, go ahead.
Hi, this is Sumit from Google. Can you speak more to the decision of having a split L2 between I and D instead of having a shared L2?
Yeah, and it's kind of repeating some things I said maybe fairly quickly before. Secondarily, when you have large code and data footprints, and you get a contention that people usually try to manage, we actually just kind of sidestep that problem. But really, the primary motivation was to then be able to separately optimize both the instruction side and the data side. You can see on the instruction side, we only have a single level large cache. We can access it with a very short latency, namely 2 cycles fully pipelined. Hard to do that if you have a shared instruction and data cache. And then on the data side, we're able to then optimize that coupling to have much shorter than what you see with most other designs nowadays in terms of L1 miss, L2 hit latency. And then of course, you can have lots of fetch bandwidth while also not compromising your data bandwidth into the L2.
Thank you.
Okay, let's do just one more, and then we'll have to go for lunch. Okay, thank you. Go ahead, Slide.
All right, this was a slightly tangential question from Tom St. John from OctoML. He says, you stated your intention to compete in the automotive compute market. Are you planning to release a variant of your architecture which supports automotive requirements like functional safety, expanded thermal operating range, etc.?
Short answer is yes. And there are similar things that if you talk about, say, the mobile market as well, that yes, they both want high performance with power efficiency. With automotive, say ASIL certifications and a whole laundry list of things. We are a good ways down that road towards supporting the kind of features needed for automotive, including getting the ASIL certifications for our first generation design.
Would that be a separate product, I think is part of the question?
Oh, yes. A derivative product, yes. Yeah. As like what you see with ARM.
Okay.
Okay.
Let's thank the speaker.